This is episode 2 of Real Analysis, a History. Last time, a bishop named Berkeley exposed the rotten foundation under calculus. You'd think mathematicians would stop and fix it. They did the opposite. Meet Euler, the man who added up infinities like they were nothing, and was right for 40 years straight. Let me put it bluntly, this man did things that would get a student failed today, for 40 years, and was almost always right. The whole 18th century, led by Euler, took just compute and don't ask why to genius level, adding infinitely many things, dividing infinity by infinity, vibing their way to the correct answer. First, the setup. In 1734, Berkeley showed the hole in calculus was real. Did the century slow down to patch it? Not even close. Euler and his peers went wilder. They treated infinite sums and infinitesimals like ordinary numbers and shoved them around freely. And somehow, the answers came out stunningly correct. Here's crime number 1. Take a sum a school kid could write, 1 minus 1 plus 1 minus 1, forever. What's it equal to? Bracket it one way, 1 minus 1, plus 1 minus 1, everything cancels, you get 0. Bracket it another way, keep the first one, then the rest cancels, you get 1. Now watch Euler, call the sum s, pull out the first one, and what's left is 1 minus s, so 1 minus s equals s, which gives s equals 1/2. 3 honest methods, 3 different answers. So what does adding infinitely many numbers even mean? You can't actually finish the addition, it only makes sense if the running total homes in on something. Walk toward a wall, each step covering half the remaining distance, 1/2, then 3/4, then 7/8. You never arrive, but you close in on 1. That's convergence. Now 1 minus 1 plus 1 minus 1, the running total is 1, 0, 1, 0, forever, it never settles. That's divergence. A divergent sum simply has no standard answer, so when brackets change the result, that's not a paradox, it's an alarm. Crime number 2 is closer to a miracle. A problem had stumped Europe for decades. Add up the reciprocals of the squares, 1 plus 1/4 plus 1/9 plus 1/16, what is it? Euler looked at the function sin x over x, which equals 0 at pi, 2 pi, 3 pi, and so on. A normal polynomial can be written as a product over its roots. So Euler treated sin x over x as an infinite degree polynomial and factored it by its roots the same way, then matched the coefficient of x squared on both sides. Out fell the answer, pi squared over 6. Was that legal? Not at all. Treating a trig function like a polynomial had zero justification at the time. But about 100 years later, Weierstrass's product theorem proved that, under the right conditions, you really can factor such functions by their zeros. In other words, Euler's intuition was right, he just used a theorem that hadn't been invented yet. Exactly like Leibniz's infinitesimals getting vindicated by the hyperreals last episode. So can you reorder infinite sums however you like? No, and here's the reef Euler kept dancing around. Take 1 minus 1/2 plus 1/3 minus 1/4, and so on. In this order it sums to the natural log of 2, about 0.69. But these same numbers can be reordered to sum to 1000, or 0, or even minus 5. With infinitely many terms, the order decides the answer. That's the Riemann rearrangement theorem, exactly the kind of move that eventually had to be made illegal. Here's the twist, Euler wasn't lucky. In the 19th and 20th centuries, mathematicians like Abel and Cesàro asked a better question, not was Euler wrong, but what should the word equals even mean? They built wider notions of summation, and under those, 1 minus 1 plus 1 minus 1 equals 1/2 rigorously, no hand-waving. Euler's intuition was, once again, a century early. It's the same story as last episode. Back then, the infinitesimal mocked as a ghost turned out to be real in a bigger universe, the hyperreals. Here, the divergent sums dismissed as nonsense turn out to be real under a wider definition of summation. The pattern is clear, what looks illegal usually isn't wrong, the definitions were just too narrow to hold it. Real analysis is half about tightening definitions to stop crashes, and half about widening them to adopt truths that were always there. And this is hardcore modern physics. Take 1 plus 2 plus 3 plus 4, forever. Ordinary addition gives infinity. But under something called zeta regularization, it's assigned the value minus 1/12. This is not a meme, it shows up in the Casimir effect. Put two metal plates in a vacuum and a real force pushes them together, a force you can measure in a lab, and its theoretical value carries that minus 1/12. The number of dimensions in string theory comes from the same sum. Divergence is useful far beyond that. Engineering and physics lean on asymptotic series, often divergent, yet take the first few terms and the accuracy is shocking, like Stirling's formula for factorials or perturbation theory in quantum mechanics. And in signal processing, a Fourier series overshoots at jumps, the Gibbs phenomenon, but Cesàro's averaging trick smooths that overshoot right out. Euler's ghost is everywhere. Beyond the present, the real blue ocean is turning divergence back into a tool. Resurgence theory pulls hidden physics, tunneling, instantons straight out of divergent perturbation series, and it's hot in quantum field theory and string theory. The spirit of regularization even lives in machine learning, where a controlled finite penalty tames a quantity that would otherwise blow up. And summation methods like Borel and Pate squeeze convergence out of divergence for high-precision computing. Euler's crimes are exactly what the series chapter of every analysis course exists to patch. First, it defines a sum rigorously as the limit of partial sums, so divergence series are simply undefined. Then it splits convergence into absolute and conditional, and drops the Riemann rearrangement theorem on you as the big scare. Reorder a conditionally convergent series and you can hit any value. Then uniform convergence sets the conditions under which Euler's free moves, term-by-term differentiation and integration, are actually allowed. The graduate sequel Abel, Cesàro, Tauberian theorems, zeta regularization, finally rebrands Euler's crimes as rigorous theory. Cambridge's Analysis I, Princeton's MAT 215, and MIT's 18.100 all run through this. One line to take away: Euler's wrong kept becoming the new definition of right. His outrageous methods weren't luck, they were intuition reaching for theorems that didn't exist yet. 3 takeaways. 1. An infinite sum only means something if the partial sums home in on a target. 2. Order matters, reorder a conditionally convergent series and the answer changes. 3. A divergent sum like 1 plus 2 plus 3 can be assigned minus 1/12, and physics measures the consequences. Next episode, the party ends, Cauchy walks in and says, "Enough cowboy math, let's define limits properly." He came to ruin the fun, and to save calculus. If you like math told as a thriller, like and subscribe for episode 3. That's the whole of episode 2 of Real Analysis, A History.